energy of the nonlinear scattering operator is the linear scattering operator. You reconstruct the potential, and then you change the problem, and you reconstruct the nonlinear part from the low energy scattering operator. Right? And then next results, also due to myself, in the case of the half line, with Dirichlet boundary condition at 0, would you please go to the next slide? So, and in this case, well, we assume just that the integral x model v of x is finite. And then again, you get the L1, L infinity, LP, LP prime estimates, right? Now, in this theorem, it was the first time that this estimate was proven under the optimal decay condition on the potential, namely that x times v of x is integral at infinity, right? Well, also at 0, but what's important here is that the integrability at infinity. And then it was discovered there that the LP prime estimate holds under the optimal decay condition, whether there is a zero energy resonance or not. Right? So this was an issue and became an issue also later on. Question was, are the stronger potential conditions in the exceptional case necessary or not? Well, the answer here is that you don't need them. And the fact that the local integrability around 0 is not needed is specific to the Dirichlet boundary condition. If you don't have Dirichlet boundary condition and the potential is not locally integrable around 0, well, there are even problems to define the regular solution, as is well known. So this is next result. So let's go to the next slide, please. Okay. And then there is Jean Bourgain. Now, in his book, Jean Bourgain, Global Solution of Nonlinear Schrödinger Equations, of 1999, well, Bourgain proposed as an open research problem to prove the LP prime estimate in 1 and 2 dimensions. And my result was obtained independently of Bourgain's proposal. Actually, my paper as a preprint appeared at the same time as Bourgain's book. I still managed to add a note in the proof concerning this proposal. And the motivation of Bourgain was the study of the properties of the set where the solution of the nonlinear Schrödinger equation blow up. So as well known, there is blow up for a finite time under appropriate conditions. This was, well, perhaps the first was Fritz John, who proved there is blow up in some Solev norm. But of course, Bourgain was asking the very fine question, what are the properties of the set where there is blow up? Are those points, are those lines, or whatever? And in his book, well, he had a theory that would work in 1 and 2 dimensions. However, there was at the time only for him the Journet result in 3 or more dimensions. And then he posed as an open problem to give a proof in 1 dimension that was actually my result obtained at the same time. Basically at the same time. Anyhow, Bourgain being Bourgain, so being a field medalist, since he posed this as a research problem, then of course this helped people, well, got quite a lot of people interested in these issues, on spite of their, of course, intrinsic importance, right? And so also the stability of solitons is important, by reasons which are similar to what happens in Bourgain's case. So if you have a solution that blows up without a potential, or you have a soliton without a potential, and you wish to study a stability, you perturb around the potential, and what you get is a Schrödinger equation with a potential. You begin with equations without potentials, but when you perturb around the solution that blows up, or you perturb around the soliton, then you get a solution with a potential, and then you need the dispersive estimates to study your equations, right? So I should say that these uncentered manifolds are even today some of the main reasons why people are interested in these issues of dispersive estimates. And then after this early result, it became a big subject, and there are many, many papers on dispersive estimates under many conditions. I will review some of them, mainly one dimension. So could you please go to next slide? Right. So then after the result, this became an active area of research, both in one dimension and in higher dimension. Also for other equations like the Klein-Gordon equation, the Dirac equation, equations with magnetic fields, discrete equations like discrete Schrödinger and Dirac equations, and also quantum walks. Now people are interested in dispersive estimate for quantum walk to study the long-time behavior of quantum walks. And then, well, I mentioned here the stability of solitons that I already mentioned. There are two reviews that you can check. References are at the end, and I already sent my presentation, as you can see, by Schlag and Fanelli. Right? So let's go to next slide. So the proof in one dimension and in higher dimensions are, fundamentally different. So since I will be mainly concerned with the one-dimensional case, below I comment only in the literature in one dimension, and only in part of the literature because there are many papers. So let's go to next screen. Next slide. So then there was at the beginning the question of obtaining better decay conditions, right? Now, then there was first a result by Goldberg and Schlag in 2004. L11 in the generic case and N12 in the exceptional case. I mean on the line. On the half line already my result gave a proof in the L11 case both in generic and exceptional cases. Then D'Ancona and Selberg in 2012, they consider L12 potential plus a step potential. So goes to 0 to the left, goes to 1 to the right. So, and then more recently in 2016, then there is a result of Egorova, Kopilova, Vladimir Marchenko, and Teschel, L11 both in the generic and exceptional cases. So this one has the optimal L11 condition as in my paper in 2003 in the half-line case. When later on I will discuss a proof, you will see how this decay appears, decay on the potential. So would you please go to the next slide? So for the spherical Schrödinger equation, there are some recent papers by Holz-Leitner, Kostenko, and Teschel, Kostenko, Teschel, and Tolosa, Holz-Leitner, Kostenko, and Teschel, again, 3 papers. And then, well, in these cases, there are issues, decay rate is different. And then the discrete Schrödinger equation was studied by Stefanov, Kevrekidis, Egorova, Kopilova, and Teschel, and Bambusi and Shao recently in 2020. So this is the discrete equations, and then please next slide. Then the discrete Dirac equation, again, Kopilova and Teschel, Kopilova and Teschel in 2017 and 2020. And then other equations, well, Klein-Gordon equation, there is my early results of 2000, then Prill in 2014, Kopilova, Marchenko, and Teschel in the same paper in 2017, where they study Schrödinger, they study Klein-Gordon. Here, well, it's Klein-Gordon, it's not a wave equation, because of course, for the wave equation in one dimension, there is no dispersion. So next slide, please. And then equation on trees, so many. It's interesting to see how this has grown since the beginning in the 90s, right? So Amari and Sabri in 2020, and then more recently in quantum walks. Quantum walks are equations that are discrete both in space and time. So it's like a classical walk, but it's a quantum version of that. There are unitary quantum walks, and there are also open quantum walks where you have a quantum walk coupled to a path, and then it's not unitary. But the case that was studied in this respect is the unitary one. So Maeda, Sasaki, Segawa, Suzuki, and Suzuki in 2018, and recently the same authors in 2020. So I am sure I am not mentioning everyone, just a few of them, right? So then the topic of my talk today is the metric Schrödinger equation on the half-line, right? And the results here are to a large extent based on results on the monograph that Vladislav mentioned. It appeared in May, actually. Have a copyright of 2021, but it appeared in May 2020. So let's consider the metric Schrödinger equation on the half-line with a general self-adjoint boundary condition. You have it on your screens. And so R is, please go to the previous slide, not so here, right? So R plus is, well, C infinity. U is a function from R times R plus into Cn, right? Or could be a matrix too. A and B are constant matrices, n times n. The potential V is self-adjoint, a matrix, n times n matrix. Dagger is, well, taking the adjoint. And I assume that I am in the L11 class, so the Fadeev class. So let's go to the next screen. And then, of course, you can state this boundary condition in so many different ways, and so many people have written about this. But for our purposes, it's convenient to write them in the following way. We require that V dagger A is self-adjoint, and A dagger A plus V dagger B is strictly positive, so no zero eigenvalue. And then H, A, V of V is a self-adjoint realization with a general boundary condition. Sometimes I will just write H or H, A, V. Right? So this is our operator. And then please go to next slide. Okay, then the theorem I wish to present has appeared in 2020 in the Journal of Evolution Equations, online first. Now, suppose the potential V is self-adjoint, is in L11, and then we do have the del PLP prime estimate. So, for the star graph with the Kirchhoff boundary condition and a potential in L1 gamma bigger than 5/2, this estimate was proven by Mehmeti, Amari, and Nikkei. In the case of a star graph with potential identically zero and general boundary condition, then there is a result 2019 by Grecu and Ignat. A star graph is well, it's a star, so you have one vector, one vertex, and a finite number of half lines, and you give the boundary condition, of course, on the vertex, and this is unitary equivalent to a metric Schrödinger operator with a diagonal potential. So it's a particular case, in the case of a star graph. So let me go then to please to next slide. So, and then the corollaries, the Stricher estimates, which are important. And you use the L1, L infinity estimate in this form. So let's QR we admissible. So 2 over Q is 1/2 minus 1 over R between 2 and infinity. Then for every phi in L2, the function T, E minus TH, PACH phi belongs to LQ of R into LR, continuous R into L2, and this space-time estimate holds, right? This is one Stricher estimates, and moreover, let I be just any interval, and let's take another admissible pair, gamma rho. If F is in L gamma prime, identity into rho prime, L rho prime into R plus, under, well, the standard condition, 1 over gamma, 1 gamma prime equal to 1, 1 over rho, 1 over rho prime equal to 1, then the function T into phi F of T, given by this integral, E minus T minus H, PF, belongs to this space, LQ, ILR, intersection continuum, CIR, 2. And for I, for a constant that is independent of I. And then there is the other estimate below, right? So why are they important? If you see the first operator, phi sub F of T, well, if you write down your nonlinear Schrödinger equation as an integral equation, this is one of the pieces you get. You get the free evolution applied to the initial data plus this phi sub F of T, and this is the one you wish to estimate, say to make a fixed point argument or some other type of argument. And then the Stricher estimates that follow from, well, in this general condition, from an abstract result of Kiel and Tau, tells you that have nice mapping property between appropriate space-time spaces that you use to study the nonlinear Schrödinger equation. So next slide, please. Okay, these results show that the LP prime estimate holds for general metric Schrödinger operators on the half line. We will see now also on the line whether there is a zero energy resonance or not, as was proven already in the much simpler case of the half line scalar Dirichlet boundary condition, right? Here, well, let's say we're in the generic case. If a just metric is invertible at zero energy, and we are in the exceptional case if a just metric is not invertible at zero energy. In the exceptional case, there is a zero energy resonance or a half bound state. And the generic case, which is simpler, there is no zero energy resonance. This is very much like in the scalar case. Instead of a just function, you have the just matrix, of course. So next slide, please. So let's go to the metric Schrödinger equation now on the full line, right? Now, a 2x2m metric Schrödinger equation on the half line is unitarily equivalent, it's the elementary result, to a n times n metric Schrödinger equation on the full line with a point interaction at zero. And the unitary is the obvious one. So we define the unitary operator U from L2R plus into C2N onto L2 of R Cn as follows. Well, for positive X, you take half of your components in your solution, the first n of them, and then, well, for X negative, just take the negative part, right? So for a vector Wallet function C, psi, psi1, psi2, T is transpose, where each one is in L2 RC. And so you take first n components and you project into positive X, then the last n components into negative X, right? And suppose the Schrödinger, the potential on the half-line is diagonal. It's V1 times V2. Each one are self-adjoint m times n metric valid functions that each one of them is in L11 of the half-line. So let's go to the next screen, right? And then the Hamiltonian is transformed into the following Hamiltonian in the full line, right, in the usual way. And the operator HR is a self-adjoint realization of the formal differential operator minus second derivative x plus q, where q is V1 for x positive and V2 for x negative. And the given 2n by 2n matrices, A and B, we decompose into A1, A2, B, B1, B2, AJ, BJ, 1, 2, are n times 2n matrices, right? Then, for the operator on the line, you get the following transmission conditions that is written here at the bottom of your screen, which actually is a point interaction on the line. So, the general, the half line n times n, 2n correspond to a n times n operator on the line with a point interaction. Right? So this is an advantage of doing the general theory of metric Schrödinger operation on the half line with general boundary conditions, because you get as well, and the general situation, the matrix case on the line. So let's go to next slide, please. Right. Okay. Then, if you use a solution of a half line, then V u of little u is a solution of the full line problem that you have in your screen, right? So you have the Schrödinger equation on the line, you have the initial data, and you have your point interaction. Now, suppose A is 0, identity, 0, identity, and B is minus identity, lambda, identity, 0, lambda just any self-adjoint matrix, then you get the equation that V is continuous, and there is a jump on the derivative of V at 0, so V continuous at 0, equal to lambda V at 0. So this is a Dirac delta point interaction at x equals 0 with coupling matrix lambda. Then if lambda is 0, you have just that V is continuum, and the derivative is continuum, and you get the standard Schrödinger equation on the line, right? Then just by unitary equivalence, transformation being local, then we get the following result in the line. So let's go to the next screen, right? And then you get your LP prime estimate on the problem on the line, right? And then there is, of course, also the Stricker estimates. Now, I am not aware of any result on the LP prime estimate for metric Schrödinger equations on the full line, and even without point interaction. And even in the scalar case, if I add point interactions, this result is actually new. Right? So let's go to next screen. Right. And then, well, maybe I just don't describe it again. Here you have the same Strickler estimates, but it's just the same as before. By unitary equivalence, the operator phi of f of t is again the one that appears in the analysis of a nonlinear Schrödinger equation with a potential, right? So this gives a complete and full solution now. I guess in the continuous case, we understand completely the dispersive estimates on the line, in the scalar case, in the matrix case, in the half line, and on the line, right? This is based on some very precise low energy estimates that I will discuss and that you will find in this monograph. So let's go to next slide. So the proof, right? Now, what is the method of proof? How do you prove this? Well, then you give a formula for the integral kernel of E minus I th PSC of H in terms of a physical solution. Now, the physical solution is defined using the Joe solution and the scattering matrix, right? Furthermore, you have to use linear algebra methods, and this is the key point in the proof is to use these methods. And for this, you need a very precise low and high energy estimates. They are crucial. In particular, they are very fine and delicate under the L11 condition. And actually, this is basically the method that was used to prove the L1 L infinity estimate in one dimension. Since my work in 2000 and 2003, all the proof, one way or another, they use this idea. And then, of course, you see why one dimension and higher dimensions are different. Scattering theory in one dimension is different from scattering theory in higher dimensions. You can do scattering theories in higher dimensions, in one dimension, by the higher dimensional methods. But then you lose the important fact that in one dimension, you have a Volterra-type equations for the Joe solutions. And the Volterra-type equation has a solution in a convergent series, which is as good and in some cases even better than explicit solutions. So if you do one dimension by the multidimensional methods, you lose a very important piece of information. So let's go to the next slide, please. And then the results that we need are in this monograph. The papers, of course, earlier, but it's a monograph presentation. So let's consider the stationary metric Schrödinger equation. Again, now psi, it's n times n matrix, or can be a vector, right? So next slide, please. And then we write the boundary condition in this form. Why this form? Well, there are other equivalent characterization of the boundary conditions. Kostrikin and Schrader. In this precise context, it was first, and Harmer. And there is a very nice monograph of Prof, Beketov, and Kolkin that do a general analysis of this type of problems and then much more general conditions. But for us, this type of boundary, the formulation is very useful, and let me explain why. So let's go to the next slide. Good. Now, you say, well, what is a boundary condition? In general case, what could that be? Well, it has to be the same as it has to be n times as the same in the scalar case, right? If you're given any boundary condition, well, you should be able to write them in diagonal form, as it is here. Minus diagonal sine of theta 1 theta n, diagonal cos theta 1 theta n, and then you have just n times the standard boundary conditions. Then you have the Dirichlet, you have the Neumann, you have the mix, or you have the Robin boundary condition. we call Nm, number of Neumann, Nd, number of Dirichlet, and Nm, number of mixed boundary conditions. So let's go to the next slide. Well, the point is that, as we show in our monograph, you can find two, just given any pair of boundary conditions, characterize as you like, but we characterize in our way because we find it more convenient. Then you can find two invertible metrics and a unitary matrix such that you go from the general form of the boundary matrix A and B to A tilde and B tilde. And under that transformation, the Hamiltonian changed by a unitary transformation. T1 and T2 are just the reparametrization of the boundary conditions or boundary metrics. M is a dynamical fact, it's a unitary transformation in quantum mechanical sense. Right? So this shows that the case of general boundary conditions is unitarily equivalent to the case of diagonal boundary conditions. Right? If you think for a while, you have to really that, right? So you could say, why do we use A and B? Why not to use A tilde and B tilde? Well, the problem is that in physics, A and B express the physics of the problem. So Kirchhoff, A and B, the ones you use, tells you that the solution is continuous, and when you add the derivatives of the different components of your wave functions, they add to zero. This is the physics of the problem. It's not probability conservation, as some people say, because any self-adjoint boundary condition conserves probability in quantum mechanical sense. So it's maybe not a good name, Kirchhoff, but it's so popular that we use it, right? So, but if you go to a diagonal form, Kirchhoff boundary conditions corresponds to one Neumann boundary condition and the rest Dirichlet. So one Neumann, the rest Dirichlet, doesn't express properly the physics. So you wish to have the more general possible form of the boundary condition, but as expected, you can always write down them as a number of Dirichlet, a number of Neumann, a number of mix, right? Now, this is technically very useful, right? For example, in the case where the potential is zero, then the proof of the L1, L infinity estimate follows immediately. It's trivial. Because you go to the diagonal representation, the transformation is local in X, and then from the explicit representation, you can solve explicitly Dirichlet-Neumann mix, and you just see in the formulas that you have the L1, L infinity estimate, much as in the case of the line without potential. So going to the diagonal form gives you immediately the L1, L infinity estimate in the case without potential. But it's not only that. It just happens that the low energy and the high energy behavior of, say, the Jost matrix, the scattering matrix, and so on, depend explicitly in the number, say, of Dirichlet boundary conditions that you get in the diagonal representation. So without going to the diagonal representation, you cannot really study the low energy and the high energy behavior. So let's go to next slide, please. Okay, this is what I just explained. So let's go to next slide. Okay, well, let me mention now the monography of Agranovich and Marchenko of 1963, which is a fundamental piece of work where they study the Dirichlet case. There are many differences between Dirichlet and general, in particular for the inverse problem. For the general boundary condition, you have to reconstruct the boundary matrices. In the Dirichlet case, you assume from the scratch that you have Dirichlet boundary condition. But well, the Jost solutions are constructed by using the standard well-known methods, and here I write them. Now, the Jost matrix is defined according to this formula. actually doesn't coincide with the definition. Well, it's somehow, there's an issue in how you define the Joss metrics here, and then the scattering matrix for the inverse problem. If you do not define it in a proper way, then there is not even uniqueness of the inverse problems under general boundary conditions. And we discussed that in our monograph. So it's analytic in C+, continuous, away from zero, invertible, R-0. And if the potential is L11, then the Joss metric is continuous, even at zero. I mean, the Joss metric, the L11 condition is only needed for the low energy behavior. So let's go to next slide. Right. And then we construct the scattering matrix that, again, doesn't coincide with the scattering matrix defined by Agranovin and Marchenko, because here, as unperturbed problem, we take the Neumann problem, they take, of course, the Dirichlet problem, and for quantum graph, which is one of the motivations here, the Neumann boundary condition is more natural for the unperturbed problem. So, well, of course, in the exceptional case, this definition is okay for non-zero k, but then it's continuous at zero, right? Then you express the Joss solution, the physical solution, in terms of the Joss solution, the scattering matrix. And let's go to next slide, please. So the physical solution, then you use to construct the generalized Fourier maps in the standard way. And for any Borel set O, well, the spectral projector is related to the generalized Fourier maps in the standard way. And then you extend to operators in L2, which are isometric. So let's go to next slide. Right. Then there are many results. Well, no positive bound state, only negative bound state definite number, no singular continuous spectrum, and the generalized Fourier map diagonalizes H. If moreover we are in L11, there is no bound state at zero, and the number of bound states is finite, just as in the scalar case. So next slide, please. And then, well, have intertwining relations, and then you get a formula for the integral kernel of the unitary evolution operators. After some calculation, you get this, you have the Joss solution and the scattering matrix. And this is the starting point of basically any proof of the L1 L infinity estimate in one dimension. And then let's go to next slide. And then following again Agranovin and Marchenko, we represent F by a transmutation operator, and these estimates are true, where sigma is integral from x to infinity of v, sigma 1, x to infinity of y, v of y, right? Standard result. So let's go to next slide. And then the idea is as follows. Well, in this paper, we decompose it in several terms, right? I will not discuss all of them. The first one, tau sub 0, well, there you have. It's just the convolution. Then there you see explicitly the fact that for this term, L1, L infinity holds. This is basically the only one you would get if there's no potential. And then the one which is more interested is this one, tau sub 3, which is convolution with this kernel time ff of c, where ff of c is the Fourier transform of s of k minus s infinity. S infinity is the limit of s of k at high energy that you have to prove, of course, that it exists. Right? And then, the next slide, please. Then what you need to prove if Fs is L1. If you know that L1 Fs is integrable, then you get from immediately that this tau sub 3 terms is satisfy the L1 L infinity estimate. And the others are somehow more complicated, but eventually this is what you need, right? And then for this you need, well, you need precise low and high energy asymptotics for the Jost and the scattering metrics. And then those you find in the monograph. So let's go to next slide. So let me discuss the small k behavior. So let mu be the geometric multiplicity of the zero eigenvalue of j on 0 and nu the algebraic multiplicity. Then you decompose j of 0 in the Jordan canonical form. You have first the chains corresponding to the kernel, so the eigenvalue is 0. So next slide. And then the non-zeros, and S is an invertible matrix. And just let's call M tilde S minus 1 MS for any matrix, right? So let's go to next slide. Yes, could you go please to next slide? Okay. And then, no, the previous one. No, the next slide, please. The next one now. Good. And then J tilde of 0, so after transformation by S, and after some permutation matrices, you just put first the zeros, then identity. And sorry?
Or to extend, you mean you want to start from a type 2 and then extend, but it's, I mean, it's not clear.
Well, I am not sure what is your question.
Not clear whether it's extendable.
Yeah, but then, I mean, it's not clear that this is an eigenfunction of a closed and...
Well, I have just a matrix. What I am doing is just a matrix, which is J of 0, and I transform it into the Jordan canonical form. This is what I am doing, right? And then, just for convenience, I do some permutation of columns and lines in such a way that I have the zeros at the beginning. This is what I am doing. Nothing more than that. Just J of 0 is just a matrix, and I go into the Jordan form. And once I am in the Jordan form, I rearrange to have the 0 first, all the zeros first. So maybe we discuss that later, because the sound is not so clear to me. So let's go to next slide. Okay, then this is the result. Now suppose that V then Selvaggion, L11, as k goes to 0, then this is the behavior, right? You see there are terms k, A1, little of k, then k, B1, A1, little of k, k, C1, little of k, D0, little of 1. And the point is that A1 and D sub 0 are invertible. The proof that they are invertible is because they are a metric representation of some operator that we prove it's invertible. Then we have a precise low energy formula both for J and J minus 1. This, of course, is in the exceptional case. In the generic case, you don't need to do this. So let's go to next slide. And then we know it is continuous, the scattering matrix, and we know that S of k is of 0, little of 1, And what is very important for us, is that we have an explicit formula. We know what S of 0 is. And this is used to prove that f sub s, so the Fourier transform of s of k minus s infinity, is actually integral. So under L11 condition, this is, somehow a delicate result, and it has an interesting history that maybe you know them. But let me repeat it in case of some younger people don't know it. Now, this issue appears in the fundamental work by Fadeev in the solution of the inverse scattering problem on the line. And they claim that this continuity in the scalar case which holds. Recall that by my unitary transformation, this also applies on the line. And he solved the characterization problems on the line by a Kravchenko method. But then later on, this was questioned by Shadam and Sabatier and by Taif and Krubovitz, who were claiming that actually in the exceptional case, it was not enough, and then that the L12 condition was needed. What is a twist of history is that even earlier than the papers, the book and the paper by Shadam and Sabatier and Taif and Krubovitz were published, there was already a solution in the book by Kravchenko. So in his book, that was in Russian, and then I guess at the time the communications were not so fluent. But in his book in Russian, by carefully avoiding the issue of continuity at 0, Kravchenko gave a solution to the characterization problem. So before the complaint by Taif and Krubovitz and Shadam Sabatier was made in their book and papers. And then also Mellin gave a proof avoiding the issue of the continuity, until eventually Klaus was able to give a proof of continuity under L11 condition at 0 energy, and to give a characterization using the continuity, right? All that was in the scalar case. Well, these results give now an answer to this question in the general metric case with general boundary conditions, so the line case with L11 potential plus a point interactions. So let's go to the next slide. And well, maybe a question. Well, okay, let me mention this, because I guess we started by 10:15, right? So the large K behavior.
Yeah, yes, we started a little bit later, yeah.
Okay, so how much time do I have?
Well, some 5 minutes, probably.
Okay, so let me say something more in 5 minutes. Let me introduce these quantities, Q1, Q2, up to Q6, that you can see in your screen. And let's go to a next slide. So if you
Можете, да.
This is the right one. Then here we have this precise estimate, right? S0 of infinity plus j of k 1 over ik plus order 1 over k squared, right? So on S0, so you see here S0 infinity, here M is my unitary matrix that appears in the transformation from general form to diagonal form. And you can see there the number of mixed, number of Dirichlet, number of Neumann boundary conditions that appear. So this other estimate is used because, well, you have somehow to be careful with Wiener arguments, because the high energy behavior is not just identity here. So this precise estimate, studying explicitly the 1 over k terms, allow to study that. So next slide, please. Okay, now there is another method that I guess, yes, I have a few minutes to discuss it. Now there is a different method to study dispersive estimates. So here we just study them directly, right? So we directly study the unitary group of evolution. Now there are very important results that I did not discuss earlier by Yashima, who introduced a different method to prove dispersive estimate, starting in 95, and now there is a recent paper, 2020, with a review of the results. Now let's extend H0 minor Laplacian, H0 plus V in L2, and suppose that the wave operators exist and are complete. But then you have the intertwining relations. And from the intertwining relations, you see that for every, say, for L function f of h, PAC of h is unitary equivalent to f of h0, in particular for the unitary group. So if the wave operators are bounded in LP, then from the dispersive estimate h0, you obtain the dispersive estimate for h. So this is another method to prove dispersive estimates. Now this method works, well, in some cases. So let's go to next slide. Now, moreover, the bounding of the LP, or the wave operator, is an interesting problem on its own. We have proven in many circumstances. However, it often fails in the presence of threshold singularities. So if n is bigger or equal than 2, not only also in n equal 1. So if you have some resonances of a bound state, well, it's not always true. Right? In particular, in one dimension, which is the case I am discussing, in my 99 paper, I proved that in the one-dimensional case on the line, the wave operators are not always bounded in L1 and in L infinity. And then you cannot use them to prove the L1, L infinity estimate. And the results just follow. Actually, this with the new techniques that I have now, this can be improved. So gamma bigger than 3/2 in the generic case, 5/2 in the exceptional case. Then the wave operators are bounded in LP, bigger than 1, smaller than infinity. And they are only bounded from L1 into L1 weak, right? Not in L1, L1 into L1 weak. And the adjoint are bounded from L infinity into BMO, bounded mean oscillation spaces. Right? So this is what you get. And moreover, in the exceptional case, if the Joe solution goes to 1 at minus infinity, then they are bounded in L1 and in L infinity. Has to be like that. Why? Because on the line, the zero potential is exceptional. And of course, if the potential is 0, the wave operators are the identity. And, well, then they are bounded. So there is a class of exceptional potentials that contain the zero potential, characterized by the limit as x minus infinity of the zero energy Joe solution, where you do have boundedness. Now, why this is true? Well, again, you would like to do the low energy and high energy analysis of the wave operators, and in the low energy analysis, there is a term that contains a Hilbert transform. And these are the mapping properties of the Hilbert transform. In the exceptional case, if the limit as x go to minus infinity of the zero energy Joe solution is 1, the coefficient in front of the Hilbert transform is 0, and then you have the nice mapping properties, right? So this Yashima method, when you can use it, is useful. Somehow the idea here is that, well, in the L1 L infinity estimate, so in the unitary propagator, there are some cancellations that take place that do not take place for the wave operator. This is why you can nicely prove the L1 L infinity estimate, but you cannot prove the boundedness of the wave operator. This also somehow shows again that these estimates are indeed subtle. So let's go to the next slide and then I finish. Yes, I wonder if you listen to me. Could you go to next slide? Hello? Oh, here. Well, then there are many other applications. Levinson theorem. Let's go very fast. Levinson theorem. The next slide. The Kreiner spectral sheet function, and then Uzlaev-Adev trace formula. So let's go to the next slide. Oh, well, then let's go to the next slide here, explain this trace formula. Okay, so next slide, please. So let's keep next slide. And then, well, there are many results. There is a characterization of scattering beta, but let's just keep moving until you will see a picture of my book. So let's keep moving several slides. So let's keep moving. Oh, here is stop. Well, okay, this is the monograph we're talking about, and well, I was recently listening to an online conference, and there was a talk by Simon where he said that making some advertisement is fine. So I hope you don't mind if I advertise this monograph that just appeared in May. And then, well, there is a complete theory there of the direct and inverse scattering for metric Schrödinger equations. Right? So next slide, please. For your attention. And then I am just a little bit late, but not too much actually.
Thank you very much, Ricardo, for a very, very interesting talk.
Okay, I hope you like it. Let me put my slide so you can see.
If there are questions, please unmute your microphone.
Yes,
I see that Pavel Exner has a question.
Yes, Ricardo, I have one. One of your main motivations for graphs, so your matrix Schrödinger equation, it's a star graph. Yeah. What about the situation when instead of a star graph, you would have a graph with loops? Say you take your star, disconnect and connect to a compact graph. One would guess that you would have dispersive estimates again. Can one say something about that?
Well, now, there is a result that go back to Kravchenko and Schrader, where they discuss the issue of writing a general graph as a product of star graph, right? And also in the book by Alexey and Kuchman, they discuss that. But so this is a hope, right? Now, if there are loops, well, so the dispersive estimate has to do with a continuous spectrum. So maybe at least under some circumstances you should have dispersive estimates. But this is actually a problem that has to be studied.
Okay, thank you.
But I don't know. I would guess that if you look carefully and there's something circumstances, they are tricky, right? Because they are very sad. You are saying that in L infinity norm has to go zero. There is no averaging possible there. So, but probably you can do that.
Okay, thanks.
Well, nice to see you again.
Thank you. If there are other questions, please. Ricardo, how much of... okay, there is another question by Anatoly Tadeev, yeah? Please. But you have your microphone unmuted, Anatoly. Your microphone is muted, Anatoly.
Okay. I want to ask a question about combinatorial graph or matrix graphs. So what is what we are talking about? Combinatorial graph or matrix graph?
Well, I am talking about metric Schrödinger operators.
Okay. Okay.
Well, but suppose
the graph is a metric graph. Okay. So not
yes.
no discrete analysis. Okay. This is okay. Continue.
And the idea, at least as far as star graph is concerned, is very simple. If you just take a metric Schrödinger operator, if the potential is diagonal, you can map that unitarily to a metric star graph, or a quantum graph, as it's called in the jargon of mathematical physics. So,
okay.
What about a more slowly decreasing of the potential at infinity?
Well, okay, I talk about optimal conditions. Optimal in the sense that those are the best conditions we know. Now, I believe they can. I guess if you have the condition, whenever we have the time, I should try to cook up an example. Maybe using, potentials explicitly, and so my conjecture is that in general they will fail. But they are optimal only in the sense that those are the best conditions we know. But I think it's possible to consider examples where they failed for potentials that they decay more slowly. Because then the properties of the unitary propagator will be different.
Okay.
Maybe to do the student problem of finding examples, counter examples actually.
More questions or comments? So thank you very much, Ricardo, once again for a very interesting talk.
Thanks for listening, and let's hope we can all meet together, well, in the near future, because how the situation is now, we don't know really.
Yes, let's hope.
Okay. Thanks.
Okay, thank you very much for a very interesting talk.
Well, nice to see you.
Okay.
Okay.
До свидания.
Покажись.
Привет и до свидания.
Пока я не...
Вот, Роланд.
О, отлично. Все прекрасно выглядят. Все великолепно.
Arrivederci.
До свидания.
До свидания.
До свидания, всего доброго.
До свидания.
Very
До свидания, всего доброго, до
И
свидания.
Коля Антоневич.
Да, а ты что думал? Тоже учиться надо, никогда не поздно.
Это точно.
Bye-bye.
Ну, хорошо, всего доброго, рад всех видеть очень. До свидания.
Thank you, Ricardo.